Good morning, everyone. We'll get started. We were looking at random noise and we took the example of a resistor. In a resistor, we have noise because if you look at the instantaneous current, it consists of whatever current is caused by the applied voltage and also which sort of represents the average flow of electrons through the resistor, plus there is random motion of electrons due to their thermal energy. Okay, so this means that the current, the instantaneous current goes above and below the nominal values that you expect. Okay, so we have to be able to first of all see how much it is, calculate its variance and so on. Because it's a statistical quantity, we have to describe it by its variance or standard deviation. Okay. Now, to be able to do that, we needed some tools. Now, whenever we have time varying signals, we find that analysis in frequency domain is easier. So that's what we do here also. You have done this, of course, for circuit analysis with deterministic signals. Now, with random signals, we need slightly different measures or some related measures where you're not looking at the exact value of the signal, but something like something related to the variance. Okay, and that quantity is the autocorrelation. Okay, that's the, instead of using x of t, the signal, and its Fourier transform x of f, you can use the autocorrelation. What is the autocorrelation? The function x of t tells you what the value is at every instant of time. That's what you cannot specify for a random signal. What does autocorrelation say? The autocorrelation says if the signal at this time is so much, how much is it some time away? We don't know what this is, but if this is so much, we can still characterize it in the as, I mean, if we know that at t equal to 1 second it is so much, t equal to 1.1 second, whether it is close to it or it could be anything and so on. So that says something about how the whether the signal is varying rapidly or something, even if we don't know what the signal is. Okay, so that's why we use this autocorrelation, and its frequency domain representation is this spectral density. Now, along the way, we needed representations of power signals, because we have signals that persist for all time. I mean, not something with finite energy. So we have, that is relatively easy to handle. You already know the definitions for energy signals: Fourier transform, autocorrelation, and energy spectral density. With some modification, we can use the autocorrelation and power spectral density for power signals as well. So that's what we did. Now, how is this related to random signals? So a random process, if you take multiple instances, like for instance, you apply 1 volt across a 1 kilo ohm resistor, and then you make 1,000 copies of it and measure the instantaneous currents through all of them. This is what they will look like. Nominally, the current will be something, and the actual instantaneous current will be different in each of them. Okay, so this is what are we measuring here? Let's say we have some voltage V naught across R naught. All of them have exactly the same value, and I'm measuring I of t. Okay. So now this extra part, if I just show only the difference between the nominal and the actual, or the actual and the nominal, that is what is we call noise. Okay. So this is noise, and let's say we call this noise x1 of t, and we have okay. So in this case, the noise would be something like that. This is x2 of t and so on. So this is, let's say, some xn of t. Okay. So that's the, those are the noise waveforms. Now we can treat each one as some known signal. Okay. So each case is a known signal and calculate its power autocorrelation function, which is defined as the definition is the same for all of them. Okay. And of course, its Fourier transform is the power spectral density of that particular signal. Okay. So we have this, and then because this is a random process, at a particular instant t, right, we can take two instants. This is t and this is t minus tau, and calculate the expectation of x of t minus tau. Okay. What this is you take the product of the values at t and values at t minus tau and average it across the ensemble. Okay. So there will be some probability density function for it, right? For this value of x of t and this value of x of t minus tau, there is some probability density value. You multiply by that and average. So even if you don't know it, this is okay because you will still be able to calculate, right? Some of you may not have taken class on random processes and may not be familiar with this, but still that's fine. Now the important thing is this. This is what is called the this is also called the autocorrelation of a random process. So now for a random process, this is what is going on, right? It is telling you we can't say what the value at t is, but what this tries to measure is, right? If the value at t is something, what is the value at t minus tau likely to be? I mean, not directly in terms of probability. Let's say the random process also can have slow variations and fast variations. So we don't know what the value is at any given time. But you can see that if it is very slowly varying, then x of t and x of t minus tau will be close to each other. And that expectation will always be positive, regardless of the value of x. It could be negative or it could be positive, but the two values are close to each other. So this will remain positive for those values of tau. But if let's say at this time you have some value and at the other instant it can have any values, positive or negative, this average will come out to be 0. So they're basically not correlated. This is measuring correlation, right? Correlation between the value at time t and value at time t minus tau. Okay, now you can see why this is a suitable measure. We knew, I mean, in case of deterministic signal, we know how the signal is varying. Now we can't say that, but at least this tells you how, in a way, how the random process varies, whether it varies slowly, whether it varies rapidly. Okay, how the values are related between instants t and t minus tau and so on. Okay, and of course, these are all closely related. They are named the same thing for a reason. And the Fourier transform of this is also called the spectral density. Now, there is a theorem that others have worked out, thankfully. It's called the Wiener-Khinchin theorem. It states that, yes? No, this Rx1 is basically I'm calculating, I'm just looking at the waveform x1 of t. I'm thinking it as a known signal and calculating this function, right? This has nothing to do with probabilities or anything like that. Whereas this expectation is at this time, you look at all the values of all these instances, okay? And at t minus tau, you look at those instances, you take the product, you weight it by the joint probability density function and average that, okay? No, it is that is the definition, okay? Like for instance, what is the expectation of anything? So let's say E of y, what is this? It is you take values of y, all possible values of y, you weight that with the probability density function at that value and integrate it over all possible values, right? This is what you do. What is this function? What is this? This is the mean value, right? So similarly, you have to take this product, you have to find the probability density function of that product and average it over all of that. Yeah. Yeah, so that's what I'm coming to. So this theorem says that for ergodic processes, essentially this autocorrelation function taken across the ensemble and autocorrelation functions of each of those signals will be the same. Okay, you understand? So this and that are the same for a certain class of processes. Right, yeah, they'll be the same, yes. So that means that if all of you will measure the, let's say you take whatever number of copies of experiments you need, each of you does the same experiment, same voltage, same resistor, you measure the noise current, okay. Obviously, all of you will be, the current waveforms will be different for all of you, but the spectral density that you calculate will be the same, okay. That's what this means. So averaging across time and averaging across the ensemble will be the same for ergodic processes. Okay. The ensemble just means collection, and then it is averaging across the collection. Okay. I gave you that analogy yesterday, right? So there are many processes which you intuitively feel fall into this category. That is, a number of you do it simultaneously or you do it in sequence so many times, you will get the same result. So this is a statement of that. Of course, there are processes which don't fall into that, but the noise process that we look at do. So this is fine for us. Okay. So what this means is now so we said that we want to typically in whenever you have randomness, you want to calculate the variance or standard deviation. So what is the variance here? What is the variance from this definition? Can you get the variance? What is it? Yeah. So it is basically when you take the autocorrelation across this ensemble, from this function you can get the variance, right? Variance is Rx of 0, which is of course the integral of the spectral density over all frequencies. Okay. Now, if you look at the autocorrelation across time, from this definition, what do we get? The mean squared value. This is what we call Rx of 0. I've used the same symbol for these two. I could have distinguished them and later said that they are the same, but just to avoid multitude of symbols, I've done this. The mean squared value is Rx of 0, right? Obviously, if tau is 0, you just get the average of x1 squared. Okay. And that is equal to in fact, let me make it. This is for any k, right? So basically, that variance of this random quantity is the same as the mean squared value. Okay. So you calculate the power of that signal, and this we can go ahead with calculations even without knowing all this, but it's good to know what you're calculating. Okay. So that means you have this random noise. You take that, let's say one of you measures the power of that noise. Somebody else sits and calculates the variance across the ensemble. You will get the same result. Okay. So this is what we'll calculate. We'll basically have power spectral density defined for all the noise processes. And then as, for every component, let's say resistor and MOS transistors, then that noise goes through the circuit and the power spectral density will get modified in some way that we'll see how to do the calculation. And then that power spectral density can be integrated to get the mean squared value or the variance. Okay. Is that fine? So it basically the value itself, the value of the noise signal itself, you can't predict, but you can predict the variance. Okay. And also, you can't, this also is helpful for measurement, right? You can't really sit around taking 1,000 copies of a circuit and then measuring variance and so on. That's not possible. Okay. So what you do is you have one circuit, you measure the noise power, that gives you the variance. Okay. Any questions? So actually this, I don't know if some of the terminology, maybe with random processes is unfamiliar, but everything else is, I think, similar to what you learned in signals and systems, right? Only thing is, instead of energy signals, we have power signals. So we have that 1 by T everywhere, so that you get a finite result. Okay. So there is not much new so far. Okay. I didn't say that it's periodic at all. No. Why is what is the where did the periodic stuff come in? Yeah, that is with infinite period, right? If you have a periodic signal, you can run this integral for one period and you will get the same answer as taking the limit to infinity. But this is for aperiodic signal. That's why you run the limit of t to infinity. This is definitely not a periodic signal. Okay. For a periodic signal, you won't have this limit t tending to infinity, right? T would be one period. But for a periodic signal also, if you calculate this with the limit t tending to infinity or only for an integer number of periods, you will get the same result. Anything else? Any other questions? How do you measure the power of any signal? Not wattmeter. Yeah, maybe a wattmeter also. So here, first of all, we are only talking about signals. Okay. So power means the mean squared value, right? However you measure it. You can plot the waveform on an oscilloscope, take the samples and then get the mean squared value. Right. That's so you are now talking about something completely different. When you are doing measurement, you are drawing some energy, right? That has to be taken care of in the measurement process. Okay. So, but now we have not even come to any actual measurement in that sense, right? If you have just a signal X and you have its mean square value, so there you are not, there is no question of power or anything. You just calculate the mean square value and that is measurement. Okay. But you are talking about the process of measurement where you have to carry out the measurement without disturbing the circuit and so on. So obviously something is delivering that. But yeah, that will be there. That is there from the circuit. Okay. Anything else? Any other questions? Okay. So now, yeah. Hmm. Huh? You will never actually go and calculate it, so don't worry about it. So basically, we will operate with only the spectral densities. Okay, that will already be given. So we just want to know how the spectral densities. I just gave you this definition, but you will never sit and calculate this uh, and so on. Okay. Anyway, first of all, noise in our case will be Gaussian, so that means that all these joint things will also be Gaussian. But we'll never do that calculation explicitly. No, first of all, if you measure enough samples, you can find out. No, one way is to, I mean, what is it that you want to find out? You want to find out the probability density function of something. So the standard way of estimating it is by taking many samples and plotting a histogram, right? If you take large enough samples, that histogram will approximate the probability density function. Okay, I mean the scaled histogram. Okay. Again, we don't have to do any of that. Our only goal, first, my goal here was to demonstrate that what you calculate from one signal as power is related to what you calculate as variance for the random process, right? That is the main thing. Okay. And we'll use the concepts of the autocorrelation somewhere, but we'll never sit and calculate the autocorrelation from the definition of the random process. Okay. We know that the probability density function is Gaussian, and then we will be given spectral densities, and that's it. That's enough. Okay. Because if you are given the spectral density, you can calculate the autocorrelation anyway by inverting the Fourier transform. That's how, if we want to calculate autocorrelation, that's how we will calculate it. We won't sit and look at the probability density functions and then calculate autocorrelation from there. Okay. Any other questions? Okay. Now, our goal is to calculate what happens in circuits, right? So first, how do we do circuit analysis? We have some signal x of t, and it goes through some system with an impulse response h, and out comes y of t. Okay. So you can calculate y as convolution of x and h, right? Now, typically we don't do this in the time domain. You can, of course. You probably will use the frequency domain equivalents, where you have the transfer function h of f, which is the Fourier transform of h of t. Okay. And then you have the Fourier transform of x, which is x of f, and this gives you y of f equals x of f times h of f. Okay. This, through the Fourier transform, if you want, you can calculate the time domain function. This is normally how we do the do circuit analysis, right? Now, of course, we are not dealing with signals x and y and so on. We have to only work with autocorrelations. Okay. So what is the relationship between the autocorrelation functions? So let's say we have Rx of tau and Ry of tau. What is the relationship between these two? What is the Fourier transform of Rx of tau? So let's say first we look at energy autocorrelation, because the relationship between the will be the same. This may be something you are familiar with. Let's say this is the energy autocorrelation. So what is the Fourier transform of this? So this is, and we want to find out the Fourier transform of this, which is mod y of f square. So what is this? Mod x square times mod h square. Okay. So the output energy spectral density is the input energy spectral density times the magnitude squared of the transfer function. Okay. Now it turns out exactly the same relationship holds for the power, by the power autocorrelation function as well. I mean power spectral density as well. Okay. So this is the energy spectral density. So by the way, given this relationship, what is the expression for Ry? So it is basically Rx convolved with RH. And what is RH? You just think of this h of t, the impulse response, as a signal and calculate its energy autocorrelation function. Okay. So this you already know, and it turns out it's very easy here onwards, which is what we'll use for calculation. The rest of it was background. So again, let me just copy this over. This can always be done. Only thing is, for random processes, we cannot find x of t and y of t. Now, if you are working with power spectral densities, you have Sx of f, which is the power spectral density of x, and Sy of f, which is the power spectral density of y, and it turns out it is Sx times the magnitude squared of h. Okay. So basically, finally, the calculation itself is simple. This is, you know how to calculate h of f for any circuit, you can calculate this. Given Sx, you can calculate Sy. And similarly, the power autocorrelation function, you have Rx of tau, which is the power autocorrelation function of x, and Ry of tau would be Rx convolved with Rh. But it's important to keep in mind that these are power autocorrelation functions, and this is the energy autocorrelation function. Okay. So basically, for calculation, this is all we need to know. But it's good to have some background where these definitions come from, what power spectral density means, and so on. Okay. Any questions here? This part is easy, right? Also, the other thing is, just like variances, if you have power spectral densities from uncorrelated sources, to get the total power spectral densities, you simply add up the power spectral densities. Okay. So if you have Z is, let's say, x plus w, and if these two are uncorrelated, and this is the case that we will see. With correlation, these calculations become very messy, and in practice, we never do this. So if these are uncorrelated, then Sz would be Sx plus Sw. Okay. Now, obviously, this means that the autocorrelations also simply add up. Okay. Any questions here? So with this background, we can go on to noise of the actual circuit components. So far, I have not actually talked about circuits, right? I just only talked about how autocorrelations or spectral densities get modified as they go through transfer functions. But we need to know how much noise is there in a resistor or a MOS transistor in the first place. Okay. Any questions about any of this? Okay. So now I've already shown this a couple of times. If you have a voltage V across a resistor R, the current is supposed to be V by R, and for a constant V, this should be just V by R like that, but in reality, you will get some signal like that. And now the total current can be represented as the current that you get from the element relationship plus noise current IN. Okay. So any this is a noisy resistor, and this can be equivalently represented as you have R, and this is a noiseless resistor, an idealized version that doesn't exist, in parallel with a current source IN. IN is that noise current. Okay. So this IN is that one. Okay. So this means that we analyze the signal and the noise as separate sources, right? Now we should know how much this IN is. Okay. It turns out the model that we use for it that is the noise current, and in practice the noise is always described by the spectral density, and in circuits by the one-sided spectral density. Okay. So this one-sided power spectral density of IN is, it turns out, a constant of value 4 kT divided by R, which is the same as 4 kT times the conductance. Okay, where K and T are Boltzmann's constant and absolute temperature. Okay. Now, if you have occasion to use two-sided spectral density, if you need it, this is denoted by SIN, right? That is the spectral density of IN, and that would be 2 kT by R. Okay, but we'll use the one-sided spectral density in most cases, right? And this the spectral density is constant for all frequencies according to the model, and such a noise which has constant spectral density for all frequencies, it's called white noise. This means constant PSD for all frequencies. Okay. I mean, the term white comes from the color which has all the white which has all the colors or all frequencies. Okay. Is this fine? Any questions? So now, what is the variance of this noise? What is the variance of this noise current? How much is it? What is the expression for variance? 0. Why? Why is the variance 0? What is the expression for variance? How do you relate it to the power spectral density? Integral over all frequencies. So what is it? Infinity, right? So integral of this over all frequencies is infinity. What is the autocorrelation function? It's the inverse Fourier transform of the power spectral density, right? So what is the autocorrelation function of, what's the inverse Fourier transform of this? A constant? Huh? Impulse, right? So if I take the inverse Fourier transform, I would get an impulse. This is a function of tau. This is delta of tau. What is the multiplier? What is the scaling factor? Huh? What is that? 2 kT by R. Yeah, it is 2 kT by R. You shouldn't do it. It's basically if it is constant for f equal minus infinity to infinity, that constant is the multiplying factor, right? So this is 2 kT by r delta of tau. But first of all, so what does this impulse, the autocorrelation being an impulse, okay, what does it mean? It is basically uncorrelated with any other, for any other time instant, okay, right? So that is, if the noise at this instant is something, and the very next instant, it can be 5 seconds later, 5 picoseconds later, it can be anything, okay. So that's what this uncorrelated means. Now, okay, that's fine, we can do all this calculation, but basically this tells you that the variance is infinity, okay. So now we also know that if you do this experiment, even if one of you does it, and then you measure this noise current, what is its mean square value? What is the mean square value of that? It is the same as the variance. So how much is that? Infinity. Does it make sense now? I mean, you measure noise current and suddenly you have like infinitely large signal. Even if you struggled, you won't be able to get a infinitely large signal. Now, this tells you that the variance is infinity, or if you measure one instance, its mean square value will be infinity. That is obviously not correct. That cannot happen. That's a limitation of this model. Okay. That is, we assume that the spectral density is constant for all frequencies, and we'll continue to assume that it is convenient, but it turns out it cannot be constant up to f equals infinity. It has to fall down somewhere. Okay. So I will show you the real model also, but this is what we will use. Okay. So in physics also you may have seen these this type of paradoxes, right? Have you heard of the term ultraviolet catastrophe? You have not heard of this ever? Oh, this is very strange. It's not taught in some statistical physics or something, some basic physics. What is it? Or you have not read like popular physics books on birth of quantum mechanics and so on? Yeah. So there is a certain distribution of power. The power of a black body goes to infinity. That was the calculation. And then somebody fixed it, Planck fixed it, and then it became finite, of course, which is the real one. So it turns out, basically, the result of all of that is this factor KT is a good approximation at low frequencies, but it's really should be H. What does this stand for? What is the constant H? It's Planck's constant, HF by okay. So what happens if HF by K times T is much smaller than 1? What will be this be? What is the approximation for an exponential if the argument is very small? 1 plus x. So what will this number be? So if in this condition, it is approximately KT for this case, but the actual one is this. And what happens to this number with frequency? As frequency increases, what happens to this? It clearly goes to 0, right? Because the exponential will, the numerator is increasing frequency, but the denominator is increasing exponentially. So it will fall down. Now, but what is the frequency at which this will start happening? So we can say, let's say, just calculate the frequency at which this argument is 1. Please do that and tell me when this HF becomes comparable to KT. Okay. So one thing that you can remember is for hand calculations, you can use KT to be 4 times 10 to the minus 21 at room temperature. What is the units of KT? What is it? Joules. Okay. KT is the energy. KT by 2 is the energy of a state in this statical. I mean, you should look up some basic physics stuff. So I think it comes out to be 4.14 or something, but this is good enough for us. Okay. So this would be 4 times 10 to the minus 21 divided by H is 6.6 times 10 to the minus 34. So it's basically, this is about 2/3. Okay. This many hertz. So we are talking about terahertz, right? So we don't have to worry about it for all any frequency, even if we are designing like 100 gigahertz stuff, we don't have to worry too much about this. Okay. Beyond that, you may have to. The only thing we will carry from here, we won't use this for calculation. It's not necessary because finally your circuit will further limit the bandwidth. You will not be, even when you integrate from 0 to infinity, the integral that you get will be a lot smaller. Only thing you need to know is we had this absurd notion of infinite variance or infinite power in the noise, and that's not true. If you integrate this, you will get a finite result that you can try. Okay. Is this fine? So the actual one will start here and then it will actually decrease, but where it starts decreasing is of the order of terahertz. So we don't worry about it. Okay. So we'll continue to use the white noise approximation. Of course, you have to keep in mind that when you want to calculate the variance, there has to be something that limits the bandwidth. Otherwise, you will get the infinite result. But that is always there in any circuit. That's always there. Okay. And as I said, even a resistor, you cannot get just a resistor. You will have a capacitor across it, which will provide some filtering and some reduction of bandwidth. Okay. Any questions here? So what do we get from this? That now, wherever, if you want to calculate the effect of noise in a circuit, wherever you have a resistor, you replace it by a noiseless resistor, which means basically you carry on doing what you are doing so far. You are not calculating noise anyway. And then you have an additional source, IN, and you calculate the effect of that IN. Okay. And that is done through small signal analysis. Noise is always calculated through small signal analysis. Okay. Is this fine? Now, of course, anytime you have a resistor in parallel with a current source, you can also represent it as what? You can have the same resistor in series with some voltage source. What will be the value of the voltage source? IN times R. Okay. The spectral density of IN, as we said, is 4 kT by R or 4 kT times the conductance. So what will be the spectral density of this voltage? Huh? Yeah. So basically, when you take the spectral density, you have to multiply the spectral density of IN by the square of the scaling factor. So this is SIN times R square, which is 4 kT R. Okay. Is this fine? And you can use either of these representations. We have done this like many times. In fact, you can see already that calculations of noise and calculation of effect of mismatch are really the same. There also you had either an equivalent parallel source or a series this thing. The value there depended on something. Here the spectral density will be given, but the analysis is the same. You will be analyzing the same circuit. Okay. What are the units you think of 4 kTr or 4 kT by R? What will be the units? What should it be? Yeah. Huh? Ampere. Yeah. So basically, what is the unit of the variance of Vn? What's the unit of Vn? volts. So what's the unit of variance of Vn or mean squared value? Volt square. So now that is the integral of spectral density over frequency. Okay. So what's the unit of spectral density? Volt square per hertz. Of course, you can say times seconds, but it makes sense to call it volt square per hertz because it is density over frequency. And this will be ampere square per hertz. Okay. And again, some values are, you should always have, as engineers, you should have a feel for values. Okay. What will this be? Again, we'll take room temperature, which is 300 Kelvin. For a 1 kilo ohm resistor, what will this be? 4 kTr, how much is it? Yeah, like I said, you can take kT to be 4 times 10 to the minus 21 joules, right? So 4 kT is 16 times 10 to the minus 21. So 4 kTr is 16 times 10 to the minus 18 volt square per hertz. Okay. Or the current noise spectral density would be 16 times 10 to the minus 24 ampere square per hertz. Okay. Now, what does this really mean? So let's say I take a 1 kilo ohm resistor and I connect it to an oscilloscope, which all of you have used, I think, in at least in a couple of labs. Let's say that this oscilloscope is ideal. It shows whatever voltage is there across the 1 kilo ohm resistor. So what will you see? What will I see? What will I see on the oscilloscope? The oscilloscope, straight line. I mean, then it's not a straight line. You'll see wiggles, right? You will see noise. Okay. Why? Yeah. But I mean, I've not connected anything to the resistor, right? Okay. The one thing is the resistor noise spectral density is independent of how much current is actually flowing through it, right? It just is related to the resistance and the temperature. Okay. So I'll see some waveform like this. Okay. So what will be the size of the waveform? The amplitude or something? Or huh? What will I see? Why microvolts? So basically, the oscilloscope will have some bandwidth. Okay. So now let's say the oscilloscope, of course, like any real system, that bandwidth indicates some frequency limitation, but it's not as though everything above that frequency is cut off. But let's assume that the oscilloscope's own transfer function looks like this, and this is the bandwidth. Okay. And let's say that we are talking about a 100 megahertz bandwidth oscilloscope. Then what will I see? So the variance of this or the mean square value would be, in that case, 16 times 10 to the minus 18 volt square per hertz times 10 to the 8 hertz, which gives me 16 times 10 to the minus 10 volt square. Okay. So, or the RMS value is 4 times 10 to the 5 minus 5 volts or 40 microvolts. Okay. So, if you will see some fuzzy trace, okay, and if you look at, if you calculate its RMS value, it will be 40 microvolts. How much will be, how much will be the height of the fuzz? What will you see? As I said, the distribution will be Gaussian, right? So roughly speaking, you will see probably from minus 3 sigma to 3 sigma. Beyond that, the occurrences are too few to see anything. So in that case, you may see some fuzz which is sort of intense in the middle, and then it gets sparser. Okay, and this would be how much? 6 sigma, which is 240 microvolt. Okay, so we have to be able to calculate, right? This is the first thing about engineering. I mean, just saying it is small, it is large, all that is not good enough. Even if you want to make qualitative statement, or you are not able to make a quantitative statement, at least you should be able to say it is much smaller than something, much larger than something, and so on. But now, because we do all this sort of abstract calculations, but it is tied to something that we actually see, right? So that you will have to understand. Okay. So if you connect a resistor to an oscilloscope, you will see this noisy waveform. Basically, that means you can't make out any shape, but you will see some sort of fuzz. Okay. And by nature, it will have a Gaussian distribution, and you can calculate its variance, RMS, etc. Any questions on noise? So now all we need is, for any noise calculation, we need the noise model of the component, and circuit analysis we already know, right? All noise analysis is small signal analysis. So the noise model will consist of the model that you already know plus some source to represent the noise. You calculate transfer functions from that noise to the whatever output is of interest to you. You can get the noise, and we'll do this in the frequency domain. Most frequently, we'll just be calculating spectral densities. You are given the spectral density of the component's noise, and from that you calculate the spectral density of the output noise, and from that you can calculate the variance if you want, or the autocorrelation function, whatever it is. Okay. Any questions? Okay then, see you all.